to alrighty. Let's do it. Find all possible recipes from given supplies. You have information about n different recipes. You are given a string array recipes and a 2D string array ingredients. The ith recipe has the name recipes of I, and you can create it if all the needed ingredients from ingredients of I. Okay. So for each recipe, there's a corresponding array of ingredients in the ingredients array. A recipe can also be an ingredient for other recipes, so ingredients I may contain a string that is in recipes. Okay. You're also given a string array of supplies containing all the ingredients that you initially have. You have an infinite supply of them. Return a list of all recipes that you can create. Okay. So for this one, let's look at some examples. So you have a recipe for bread, and the ingredients is yeast and flour. So you have the supplies. You have a supplies list. Supplies is yeast, flour, and corn. Okay. They don't really. You can. Okay, I see. And the supplies is your list of ingredients that you have. Okay. I think so. Here the recipes are for bread and sandwich. You have yeast and flour. For the bread, yeast and flour is needed for bread, and the sandwich needs bread and meat. You have yeast, flour, and meat, so you should be able to. You should be able to make both the bread and the sandwich. Alright, and here for burger you need yeast, flour, and meat, and interesting. For burger you need for burger you need sandwich, meat, and bread. And then from the ingredients you can make the bread and you can make the sandwich, so therefore you can make the burger. Okay. Quite interesting. So you have some baseline ingredients which can combine to make certain recipes, and the recipes can refer to other recipes as part of their ingredients. So how to approach this? So this kind of feels like a flooding deal where you start with some spots that have water, like that would probably be the yeast, the basic supplies, and there's going to be some connections between those nodes which have already filled with water and other nodes, and the other nodes would be like maybe bread is connected to the yeast and flour nodes, in a hierarchy. So the bread is the parent of yeast and flour. Or you can think of the other way around. The bread is the child of, no, the bread is the parent of yeast and flour. And the children are flooded, then the parent gets flooded. And then like burger is the parent of bread, bread, sandwich, and meat. So this feels like a flooding graph deal. If all your child nodes are filled, then the parent node is filled. Question is how you traverse something like this. So you first fill all your nodes that are children, and then you look at their parents, but the parents themselves can refer to each other. So parents themselves can refer to each other. So how do you order when you look at the parents? I think you need at least a graph here. So I'm going to start with default dictionary to do the mapping. And this will be for each, okay, so I'll say basically each item, which can be an ingredient or a recipe, is a node in graph leaves of the tree of this graph will be ingredient nodes. Parents will require their children nodes to be we'll say on in order to turn on. Okay, so create graph mapping parent with children nodes using a basic dictionary. So for each node, so how do I want to do this? Each node, which is going to be so if you have a recipe, so for each recipe in your recipes array, no, actually for each index. So the indexes can be the same for the length of the ingredients in recipes. So say we'll have n recipes, length of recipes, which is the same thing as length of ingredients. For each for each index in the range of n, the recipe will be the ith value here, and then the graph of this recipe is going to equal the, I guess this doesn't need to be a default dictionary, it just needs to be a dictionary. Yeah, we'll just equal ingredients at this index. Maybe it just needs to be a dictionary. Okay. And how do you know the correct order of traversal so that you go from like lower ingredients to higher ingredients? I wonder if you can have like self-referring ingredients like or recipes, like a recipe that's a cake that requires cream and a recipe for cream that requires cake. I guess it probably can't have that. So how to do this? You have some baseline group of recipes. So maybe obtaining all ingredients that you initially have, and you have an infinite supply of them. Turn list of recipes that you can create. What if you had a stack, or more, what if you had a queue, where in your queue you go to each recipe node, and you're going to go to each recipe node at most twice. So what's going to happen is at each node that you go to, you see if this recipe can be created based on like some set of ingredients that you've compiled. If there's an ingredient that is not found, then you add it to the queue to be processed first, and then also add to the queue at the so you add to the front of the queue the missing ingredient, and you add to the back of the queue your current ingredient. And so you're always trying to process the things that you need. And if this is the second time that you've come across this ingredient, then either all the ingredients should have been, figured out to have been possible, or it's not possible. So for instance, let's say you had A, B, C as your baseline starting ingredients, and you had a recipe for X that required A and D. So initially your queue will be A, B, C, and X. So your starting ingredients and any recipes. And actually, let's say X is made of A and D is made of B and K. So your queue is just arbitrarily like A, B, C, X, D. All your starting ingredients plus your recipes. So then what you do is you process it one at a time. So you process A. A is the baseline, so you don't really need anything. So A is now part of your. So you keep track of a set of possible items. So any basic starting ingredients is part of the set, so A, B, C. So then when you process X, you look at X, and the recipe for X is A, D. And what you do is you see if it's already there, see if it's already part of the possible items, which it isn't, D isn't. And what you do is you would add D to the front of the queue and X to the back of the queue. So the queue becomes DDX. At which point, I mean, if you're not, I guess maybe you just need to put yourself to the back of the queue if it's the first time that you've seen it. Because because the other recipes, no, the order of operations there is wrong. I think you need to put the ingredients that you need in front and yourself in the back. Because if you just put yourself in the back and you put like is DX, it could be that let's say D requires G. Say D equals CG. So in that case, or no, let's say D requires, or K requires CG. If you just put yourself in the back, then it's possible that you get into a situation where you figure out that you have something after, but only process it later on. Yeah, so you need to add yourself. You need to add all the ingredients that you need to the front of the queue and all the ingredients that your current ingredient into the back of the queue. So for a queue in Python, it's going to be a deck, a double-ended queue. And we're going to start off with the list of the set of all our ingredients, no supplies. I guess supplies is already a list. And then we're going to add to this let's have a set for the stuff that we have. I don't know, have is equal to our a set of our supplies, and then for each ingredient we need to, or for each recipe we need to add it to the supplies. So I think maybe supplies plus recipes. Let's go and just print that out to make sure this works. Okay, so our supplies is yeast, flour, corn, and the recipes is bread. Good. Yeast, flour. So there could be duplicates, and that's fine. Yeast, flour, meats, recipes is bread, sandwich, burger. Okay. And I think we need a scene set as well. Yes, if we've seen something already, then we don't want to try to match it again. Scene is going to be an empty set. Well, scene should be an empty, or it should be a set of supplies, or just be empty set. I think it should be a set of supplies. Alright, I think that's fine. So for each, let's go ahead and create an answer array for each recipe. Is it going to be for each recipe, or do I just need to process the deck? I think I just need to process the deck. So while there is anything in the deck, we're going to pop left. So the item is going to be deck.popleft. If the item is in, if we have the item, then just continue, which is going to happen for the starting ingredients. Otherwise, what we're going to do is say seen. We've now seen the item. Wait. We haven't seen. If we don't have the item and we've already seen it, then this is not good. So if item in scene, then we just don't have the item. Okay, and that after, I guess you can consolidate. I'll consolidate logic in a single OR in a bit. So if the item, and now we say that we've seen the item, and this item is something that we don't have. So we're going to look through the ingredients of this item and add them to the front of the queue if we don't have that ingredient. So for each item in child in the graph for this item, we're going to add to the front if this item child let's see. It's possible that all the items, this could have something where everything there is where you finish. So I'll say missing is equal to false. If the item child is in is already in stuff that we have, then continue. Otherwise, it's going to be some missing ingredient. Otherwise, it's going to be missing ingredient, and we need to put the missing ingredients in front. So deck.append left add to the front of the queue this item child. And that's it. Okay, so, and also missing is, there's the missing ingredient. After the loop, we will go ahead and say if there was any missing ingredient. If there wasn't any missing ingredient, then we have this thing. If missing is false, then have.add this item. Else, we're going to say that we're going to process again one more time. So deck.append The append by itself is putting it to the back end of the queue, double-ended queue. And this is going to be the item. So we're going to process it one more time. So what happens in the case where, what would happen in the case where you miss dealing with a sub-ingredient that appears twice in your deck? So your initial deck is, let's say, ABC XDK for ingredients and recipes. So X is going to, when you process X, which requires AD, the queue would be ADDK, and then X again. And then when it processes A is already, it already has A. When it processes D, it'll put BK on the front. There's still another D. There's still another K, another X, and another D at the very end. Q gets pretty long looking. And then processes B, B is already there. When it processes K, it does CG, and then another K at the end. And then when it processes C, it's there. When it processes G, let's say G is impossible. So does this go infinite? So it has the item. If there's something missing that adds it to the back. But if it's a missing ingredient that gets processed but doesn't have a recipe for it, I guess it's possible that the item itself is empty. So I think this might be a default dictionary of list. Okay. Okay, I think that's fine. There might be a little bit of redundancy in this now that I look at it, but I might optimize that afterwards. For each recipe in recipes, we'll say if this recipe is in what we have by the end, then answer.append this recipe, and then return answer. All right, that worked. And left is all lowercase. Okay. All right. What do we have here? So the recipes are these, ingredients are these. And I didn't figure out that I can make TOKFQ. Alright, so it's 1, 2, 3. Let's go ahead and do a small print here. Print the recipe and the recipes at this index. Alright, so TOKFQ, it's self-referring, is that it? No way. No, the recipe's at this index, sorry. It's going to be the ingredients at this index. Ingredients is misspelled. Alright, so TOKFQ requires BXGM. So this one requires these three, and I assume these three are sub. So we is a base component or base ingredient. SGP, XGP is also a base ingredient. Oh boy, and this is base ingredient. So how is it possible that this wasn't determined to be easily made? Okay. So we have our deck. If the item is something that we have, then we continue. Or if we've already seen the item, then we need to go on. Seen is adding the item. Missing is initially false. So for every item child in the graph of this item, so initially, let me go ahead and just print out the initial deck. So the initial deck is this. Because talk FQ requires BXGN M. Okay, so when we process this, oh, I see. When we process this, we put the ingredients for BXGNM in front, and we also put BXGNM in the back. Wait, do I want just a stack? Do I just pop onto this? Do I just put it all in front? Never put it in the back side of this queue? Because we need to process BXGNM completely before we process TOKFQ. Yeah, I guess maybe I just need to add it to the front. So add so you add yourself and you add everything you add yourself and then you add everything that is a child of you. Okay. So deck.append this item. Append left. That's a weird way of doing it though. Shouldn't that be a stack then? So the stack has an item, and then every time you see an item on the stack, you add. Every time you see an item on the stack, you add the stuff that it that creates on the stack. Yeah, this shouldn't be a deck, this should be just a stack. But the stack should be in reverse order, so the recipes should be in front of the stack. Stack is equal to recipes plus supplies. And while there is a stack, I think you do the item. Sure, you pop the item. So stack.pop. While you have the item, keep on going. If you haven't seen the item, whatever. Keep on going then. Otherwise, scene.add the item. Missing is false. And then you actually need to add the item again onto the stack. So stack dot append item. Yeah, you need to add the item again. Yeah, this is just the most straightforward way. For each child, you add it to the stack, and you track whether or not you've added any children. And then if the thing is missing, still, if there's nothing missing, then go ahead and add the item and just remove the item from the stack as well. Stack.pop. Otherwise, this is not needed. Have the item, pop it. Okay. No, it doesn't really work. Excellent. So let's go ahead and print out the stack. I guess it doesn't really detect it very well. Let's see, so the second time through, the second time through it doesn't really process it, right? So if you've seen the item, once, the first time you see it, you put it on the stack again, and you put the children on the stack again. If you've seen the item already, then you do need to do a check on whether or not all the children are there now. You can do 1 second check. But then you would have to do that each time? That doesn't make sense. If item is seen the first time through, you add the ingredients of the item, and the second time through you just need to verify that the item ingredients are there. Okay, so for each item child in the graph of the item, if for each child in the graph of the item, if this item child not in have, then then you just need a break. The item isn't have. We'll just have a set for have not. And not and item not in have not. What is the syntax for not in? Is it not in front of the in, or is it? Okay, yeah, not in front of the in. So item is in have or not in have not. Okay, so if you've seen the item and then every ingredient that you have for this item, if this item child is not in there, then I can say the item is this item is added to the have not. And then break. And then afterwards, if I did break, I guess I need another missing here. Do I need another missing here? Maybe I shouldn't be adding this stuff here when so the first time through, I add the ingredients of it onto the stack. I guess I add the ingredients of it onto the stack. I guess I don't need to track. I don't need to track whether or not I have the item here, because I do that on the second pass. Okay, so if we haven't seen it, then we just add this item and everything that it needs onto the stack. So missing, I just can't track missing here. I shouldn't be tracking missing here, it would be redundant. So if we don't have the item child appended onto the stack, okay, just append the children itself onto the stack. And then the second time through, we do need to track whether or not something's missing. So for the item children of the graph for this item, I guess the have not was just a confused way of handling this. Okay, so missing is equal to false. Reach item child. If that child's not in have, then we break. Actually, say missing is equal to, yeah, false. We say missing is true and we break. And then after the for loop, if the missing is true, then, or missing is false, then Yeah, then we need to say that we've processed this thing. We do need a set for have not. We do need a set for have not. And then have not add this item. Okay, I think that logic makes sense. So either we have an item or we don't have an item. They're going to be in one of those two sets. If we haven't seen the item, then we do this code. And if we have seen the item, then we need to make the determination whether or not we have this or have not this based on having processed its children. Okay. Yeah. This is not comparison. If the item is in have or the item is in or item in have not. Oh, if we've seen the item, oops, if it's missing is false, if missing is false, then we say have it has the item actually. This is wrong logic. Have dot add this item, else have not dot add this item. Alright, so it worked on this case where I was testing on. So what's wrong with this? Bread is made of yeast and flour. Okay, so we push bread onto the stack, and then that pushes bread, yeast, and flour onto the stack. Flour, item child should be I mean, it should be saying that it's missing the flour, no? So for each item, if the item's in scene, let's go and just do a print here. This is a scene check, and this is going to be item, and this is going to be so scene check for this item. And what do we have when we do the scene check for this item? We have yeast and flour. Scene check for the flour, there's yeast. Okay. So somehow when we did the scene check for the flour and only yeast was there, we added flour to the stuff that we have. So scene check for the flour. Flour doesn't have any children. By default this thing should be missing. That doesn't make sense. By default this should be missing I guess if this thing has no recipe for it, then this thing has to be missing. So I think if the item isn't have or the item is have not or item isn't in the graph, there's no recipe for it. In which case this no longer needs to be a default dictionary. I think this could just be a the length of the graph of this item is 0. Okay. There's no recipe for this item. Okay, that worked. Okay, not bad. This seems to be on the wrong end of this distribution. This should still be 95% runtime. I think there should... Okay, let's go and get rid of the print. Prints probably do take some time. Or not. You take 0 time. No, they did take time. It took a fair amount of time, like 90 milliseconds. But the answer still is pretty much the same. Okay. How to optimize this? So we have 2 sets for have and have not. We also have a set for scene. Do we need the set for scene? Yeah, I think the scene is just a check to see whether or not we can make the declaration that we have it or don't have it. So if the item is 0 in length for its recipe, then we just skip the item. For each item in scene, so if we don't have the item, we add the item to the stuff we see. We append the item and its children to the children that we don't have to the list. I guess you could yeah, okay. I guess if the item child is in have not, then you can also skip it. So this logic here, if the item is in have or have not, or in has the length of that 0. Okay, I'll just make a function skip. Skip child. This is going to be a child item child. This can be return whether or not the item child is in have or the item child or the item is in have not or the length of the graph for this item is 0. So if we okay, we'll just call the skip item skip k. K is in have or k is in have not or k has a length of 0 for the recipe of it. So this logic is just going to be if we skip child k, skip skip this item, then continue, and then also here if we skip this item, then continue. Otherwise we do need to add it. And then if we have seen the item, I'm going to assume that it's missing, or we're assuming that's not missing. And for each item, child of that item, if we don't have it, then it's going to be, well, why don't I use have not here? Why do I use have not? Well, I need to have because the baseline ingredients are in the have thing. Yeah, that's fine. That's fine. I feel like there may be a consolidation with the have not set. Like maybe I should be able to skip having a have not set. For the length of the graphic k equals 0. See if that does anything, possibly nothing. Actually slows it down. Excellent, excellent. Yeah, that actually slowed it down. Oh. I think there might have been some optimization here, but I'm not gonna try. I'm not gonna bother. Okay, so back to basically the summary. We basically track what ingredients or what items we have and and don't have with set. Use a stack to go through all items, literally all the items. I think in any order you place them onto a stack, they should still work. And for each item we haven't seen, add to stack its ingredients, if any, and like mark that we have done that, kind of mark that we've seen it. And then for each item we seen, check to see if its ingredients are still missing. So by using a stack, you're enforcing that add onto a stack itself. So basically you're using the stack to make sure that something that we haven't seen gets processed twice, or its ingredients gets processed and then itself gets processed. So if you have let's say a recipe for X that requires A, B, and C, and let's say you process X first on the stack, and A, B, C was, so this is the front of the stack, right? If you have the stack and you pop X off, and x requires, let's say, AB, then you put on to the stack again x and the A and then B. And then you process the B, you process the A, and then you process the x a second time. At that point, you know that x can be created. All right, time complexity is going to be, so you have n recipes. Let's say you have n recipes, and each recipe has, well, the recipes are the nodes, and the number of recipes, and the total number of kind of connections between various recipes or your edges. Here you're pretty much traversing everything one time, I think. So I think it's going to be like O of n plus m things you have to do, because each time you look at something, you look at it again, so it's like 2n. And for each connection between that and something that you have, something that it is a child of it, you do it once. So go through each recipe and each connection to its ingredients. Pretty much once, maybe twice. Space complexity is going to be, you have a hash map. Size of hash map is also the size of the number of nodes and the number of ingredients. So O of n plus m as well, I think. Store all nodes and edges in map